Hey, what's up, you guys? So in our previous videos, we covered questions through 1 through 7. And in this video, we'll proceed with question 8. So this one right here. Okay. Now, before diving into the solution, let's start with our routine review of the steps to approach the problem. And like we mentioned earlier, this practice, this session, this review routine session we have is to help us stay focused, follow a clear path, and confidently reach the correct answer. Okay, so let's go ahead and do that. So our first step is to substitute power series representation, y prime, and y double prime into our main differential equation. Now we have completed 7 problems so far, so we're already familiar with the power series representation for y prime, and y double prime. Our second step is to match the exponents or the powers of x to n. So we need to make sure that all the x's of the multiple power series that we have, they all have the power of n. And then our third step would be shifting the indices of all the power series we have. Okay, and remember the third step comes after the second step, so we will try to shift them after we transformed them so that their powers or their exponents have been transformed to n. Okay, and then like I said earlier, I will always keep the larger index, so the power series that has the largest index will stay as it is, and we will try to shift the indexes of the power series which has a smaller value. So the smaller value starting index power series, they get shifted. Okay, and then we have our fourth step, which is combining the series to 1. So after we have performed our second step, that is making sure that all the powers of the power series has the power n, and also all the indices of the power series start from the same index, then now we can combine them into 1. And after performing the fourth step, now we will find the coefficients, okay, and we use our recurrence relationship in order to do that. And then right after determining the coefficients, we can finally find the general solution. In this form, I've constantly applied these steps to every problem I've solved, so all the problems in section 4.1 follow the same approach. So without further ado, let's dive into the problem. So in today's problem, we have y prime plus xy equals cos x. All right, so our first step was to represent all our y's into a power series. All right, so let's go ahead and do that. So we already know my y is summation n equal to 0 to infinity a sub n x to the power n, and you'll already know this goes under a red box. And then I have my y prime, which is summation n equal to 1 to infinity a sub n times x to the power n minus 1, which goes in our green box. Now today's problem doesn't include our y double prime, which means we do not have to use our y double prime. Okay, we don't have to write that over here. So let's go ahead and do that. So my y prime was summation n equal to 1 to infinity a sub n times x to the power n minus 1. And then I have my plus, and then there's an x, and then now I can use my y, which is n equal to 0 to infinity a sub n times x to the power n, goes a black bracket. Now, at our right, we have something very interesting, okay? Something we haven't really dealt with in our previous videos, which is cos x right here. Let me use a different color, this one right here. Now, there's also a power series representation for our cos x, okay? I'm going to write that over here. So this is basically summation n equal to 0 to infinity negative 1 to the power n, okay, and then x to the power 2n divided by 2n factorial. Next, I'm going to distribute my x with my second power series, okay? So I have summation n equal to 1 to infinity a sub n times x to the power n minus 1. And then I have my plus, and then the x gets multiplied. So I have summation n equal to 0 to infinity a sub n times x to the power n plus 1 to be equal. And then now I'm going to expand this power series, so which means that I will write all the terms for different values of n, okay? So when n equal to 0, then this entire thing is just 1. And then when n equal to 1, this entire thing becomes x squared by 2 factorial. And then when n is equal to 2, then this entire thing becomes x to the power 4 by 4 factorial. And then when this entire thing, when n is equal to 3, then I have my negative x to the power 6 by 6 factorial, and then so on. Okay, so this is what it looks like when we are expanding our cosine function. All right, so now moving on to our second step, which was making sure that these powers are equal to n. So let's go ahead and do that. So I'm going to first transform my first power series, which is n equal to 1 to infinity a sub n times x to the power n minus 1. And I am going to transform this so that the power of x is now n. Okay, so if you do that, so I have just an n. And so if you observe clearly, all we need to do is add a 1. So our negative 1 and positive 1 gets canceled. So I'm just left with n, right? So that means all I need to do, I'm going to add 1 to all my n's, which means that my a sub n now becomes a sub n plus 1. And then my n now becomes n plus 1. And since all my n's in my power series has increased by 1, that means my starting index will now decrease by 1. So instead of starting from n equal to 1, it's going to start from 0 to infinity. So now that's what it looks like when I have transformed my first power series. Now I'm going to transform my second power series so that the power is also n. So I have a sub n times x to the power n plus 1. I'm going to transform then. I'm going to use a different color. Let me use, yeah, I think that's a good color. Okay. Whoops. All right. So I have x to the power n. Yeah, so this is what I want. I want to transform my n plus 1 to just an n. So all I got to do is subtract 1 from my power, and I can see that the positive 1 and negative 1 gets canceled like the previous one. So all I need to do is subtract 1 from all my n's. So that means my a sub n now becomes a sub n minus 1. And since all my n's has decreased by 1, that means my starting index will now increase by 1. So instead of starting from 0, it's going to start from 1 to infinity. Okay, so this is what it looks like. So let's now write our transformed power series. Okay, so again, using my exceptional green color. Okay, so I have summation n equal to 0 to infinity a sub n plus 1 times n plus 1 times x to the power n. Erase this little mark. Okay, so and then I have my plus, and then again I'm going to write my transformed second power series. So I have summation n equal to 1 to infinity a sub n minus 1 times x to the power n, and then writing my expanded power series for my cosine function. Even though I'm going to run out of space, it's fine. This is not the first time that it happened. Okay, 6 to 6 factorial, and then so on. Okay, so I can see that my powers of my x are now n now. So that means we have successfully done our second step. Now we're going to move on to our third step, which was making sure that my indexes are the same. Okay, so I can see that our second power series has a large starting index of 1, so it remains unchanged, right? So, but our first power series has a lower starting index, that is n equal to 0, so we need to shift it to match the starting index of n equal to 1. Okay, so again, all these adjustments ensures that both the series align properly at n equal to 1. Okay, so to shift the first power series to start at an index of 1, we need to write the term for n equal to 0 separately. Okay, so let's find what our n equal to 0 turns this power series to. So it's going to be a sub 0 plus 1 times 0 plus 1 times x to the power 0, which gives me a sub 1. Okay, so I know that my n equal to 0 term is a sub 1. So now we can write that separately. And then finally, we can start our index of our first power series to 1. Okay, so let's go ahead and do that. So I have n equal to 1 to infinity a sub n plus 1 times n plus 1 times x to the power n. and then I have my plus, and then my second power series, which doesn't change. So I have summation n equal to 1 to infinity a sub n minus 1 x to the power n, and then just writing out what we've got at our right-hand side. Okay, so now if you see, we have adjusted the exponents to have powers of x as n over here and here. And we've also shifted the indices, so both power series start from 1. Right, so now we're ready to combine them into a single power series, okay? So with matching powers and starting indexes, we can proceed to merge them, okay? So let's go ahead and do that. So I have a sub 1 plus summation n equal to 1 to infinity x to the power n, and just rewriting the leftover terms. So I have a sub n plus 1 times n plus 1 plus a sub n minus 1 bracket, and then whatever we have gotten for our right-hand side. Okay. 4 minus 1 by 6 factorial x to the power 6, so on and so on. Okay. So now our fifth step was to find the coefficients for our a's, right? So to be able to do that, the first thing we're going to do, we're going to look at our first term. We have at our left, which is a sub 1, and I can see that my a sub 1 is a constant. There's no x attached to it, right? So I'm going to write my a sub 1, and I want to see what the possible value a sub 1 could be. So I'm going to look at my right, and then I'm going to look for my constant, right? Just so it matches with my a sub 1. And if I look at my right, the only constant I've got is this 1. So I can assume that my a sub 1 is equals 1 because both of them are constants, okay? In this equation, a sub 1 is the only constant terms as it stands alone without x attached to it, right? All other terms involve x, and that's why it represents coefficients for different powers of x, okay? So to find the coefficients for different powers of x, we will use this power series, okay? And we'll try to match each term with the corresponding coefficients on the right side of the equation, okay? So for example, when our n is equal to 1, our power of x is just 1, okay? And if we look at our right-hand side, the cosine doesn't have a coefficient for x when the power of x is 1. It doesn't have any coefficients, right? We don't see it. We have the coefficients for x squared. We have coefficients for x4, x to the power 4. We have coefficients for x to the power 6. So we can see that it's an even function. So all the powers of x would be even. So this implies that when my power of x is 1, this coefficient will be 0, okay? So let's just rewrite that. So I have a sub n plus 1, and my n is equal to 1 now. So I have a sub 1 plus 1 times 1 plus 1 plus a sub 1 minus 1 equals 0x. Again, this is because at our right-hand side, there's no coefficients for x. When when our power of x is 1, it's going to be 0. There's no x over here. So that's why I can write that as 0x. Okay? So taking out all the x's and simplifying this, we have 2a sub 2 plus a sub 0 equals 0. Now, I have 2a sub 2 and a sub 0. So far, I just know the value of a sub 1, okay? But for this one, we don't know either of the values, right? So again, remember we said that if we have our second differential equation or first differential equations, we will have an arbitrary number if we are not given any initial values. So in section 4.2, we are not given any initial values. So we will have arbitrary numbers. And conventionally, we always use our a sub zeros as our first arbitrary number. And depending on what order of differential equation we have, we can have multiple arbitrary numbers. So in this differential equation, it is just our first differential equation. That means we'll have our first arbitrary number. We will just have one arbitrary number. So that will have to be a sub 0, okay? So that means my a sub 0 is arbitrary. Okay, so now I can find what my a sub 2 is, because now I know that my a sub 0 is arbitrary. It's variable. It can change, to anything. So I can just write that as a sub 2 equals negative 1 by 2 a sub 0. Okay, so I have my a sub 0 as my arbitrary number. I have my a sub 1 as 1. And then now I have my a sub 2, which is negative half a sub 0. Okay, so now let's go ahead and find the rest of the terms. So when n is equal to 2, then I have my x squared, which is a sub 2 plus 1 times 2 plus 1 plus a sub 2 minus 1. Okay, so now I'm going to look at my right and see what coefficients do I have for x squared. And if I look carefully, I can see that this is what I have when my x has the power 2. Okay, so let's write that. So I have negative half 2 factorial x squared. Okay, so now taking out the squares, so just have 3 a sub 3 plus a sub 1 equals minus 1 2 factorial, which is just 2. Just write negative half. Okay, so now I know what my a sub 1 is, which is 1. So let's just plug in the value. Then I have negative half, and taking out, shifting my plus 1 to my right hand side, so it changes the sign. So I have negative 3 by 2, and doing some more algebra, I'm left with negative half. Okay, so this is the value for my a sub 3. Okay, so let's find for n equal to 3. Again, then when n is equal to 3, then my power of x is 3. And then I have a sub 3 plus 1 times 3 plus 1 plus a sub 3 minus 1. Again, remember that my cosine is an even function, so all the powers of my x would be even. Okay, and clearly my x cubed, the 3 is not the power of 3. This is not even. Okay, so that means the coefficient will be 0. And again, if you have doubts, you can go back and look at my right, and I can see that there's no x cubed. Okay, and there's no coefficients for x cubed. Okay, so that means this is going to be 0 x cubed. Okay, and taking out all the x cubes and then simplifying it, I have 4 a sub 4 plus a sub 2 equals 0. Okay, and I already know what my a sub 2 is, which is negative half a sub 0. So let's plug in that value over here. So I have 4 a sub 4 minus negative half a sub 0 equals 0. And then isolating my a sub 4, I have 1 by 8 a sub 0. So this is what my value is for a sub 4. Okay, now this question wanted us to generate 5 terms. So let's find another term when n equal to 4. Then my power of my x is now 4, which is even. So I have a sub 4 plus 1 times 4 plus 1 plus a sub 4 minus 1. So I'm definitely going to have the coefficients for a sub 4. So now I can see that this is my 1 by 4 factorial. So let's write that. So I have 1 by 4 factorial x to the power 4. Now taking out my x4s and simplifying this, I have 5 times a sub 5 plus a sub 3 equals 1 by 4 factorial, which is 24. Okay, and then I already know what the value of my a sub 3 is, which is negative half. So just plugging in that value over here. So I have 5 a sub 5, and then I have negative half equals 1 by 24. And then doing some algebra, I can find what my value of a sub 5 is, which is 13 by 120. Okay, and this is the value for my a sub 5. So now I have the coefficients for 5 terms, all right? So now we can write our solution. So our solution would look like a sub 0, again, this is an arbitrary number, okay? And then I have my a sub 1, which is 1. Then can't forget the power of my x. And then I have plus, now my a sub 2, and my a sub 2 is negative half a sub 0. So I have negative half a sub 0 x squared. And then I have my a sub 3, which was just negative half, then x cubed. Then I have my a sub 4, which is 1 by 8, a sub 0, x 4. And then finally I have my a sub 5, which is 13 by 120. That is x to the power 5, okay? And then so on. Now, you can leave the solution as it is, all right? If you want to get rid of these brackets, okay, you can do that too. So if you just want to get rid of the brackets, I have a sub 0 plus x minus half a sub 0 x squared minus half x cubed plus 1 by 8 a sub 0 x to the power 4 plus 13 120 x to the power 5, and then so on. Now again, I can see that I have alternating terms for my a sub zeros, right? So if, again, you can leave this answer as it is, all right? And then if you want to group them, like we usually do in all our problems, you can do that as well. So for the folks who want to group them, we can do that. So I have a sub 0. So I have 1 minus half x squared, and then plus 1 by 8 x to the power 4, and then so on. And then I have my constants. So I have x minus half x cubed plus 13 by 120 x to the power 5, and then so on. Okay, this is my solution. All right, hope you guys enjoyed watching this video as much as I enjoyed making them, and I will see you guys in my next video. Bye.